Welcome to Study Loop.
Okay, we have two identical spin one particles in the same that are both in S states, and they're identical. So because they're in S states, that means that the space part of the wave function is symmetric. And that tells us the angular momentum also has to be symmetric on interchange of our particles. Okay, because they're spin one, which means that they're bosons, so they have to have symmetric wave functions in general when we interchange the two particles. So we're interested in two spin one particles, so I'm going to go to the table of Clebsch-Gordon coefficients. No reason to calculate them myself. And let's just look at what they are. We might be able to guess in advance, but so to the left of the equal sign, it's always going to be labeled by the total angular momentum, its total spin state, and its m value. To the right of the equal sign, I'm going to label states with the z component of angular momentum of our individual particles, m1 and m2. Okay, so first of all, we're going to go through j equals 2. So there's all the j equals 2 states. And one thing we can see right away is that they are symmetric. If I interchange the two particles, the sign of the wave function stays the same. If I go to the j equals 1 state, typo there. I'll correct that in just a moment. And we can see that all of those states are anti-symmetric. If I look at the right-hand set of states, if I interchange the first slot and the second slot, the wave functions change sign. So they're anti-symmetric. And then the 0, 0 state, there's only one of those. And it also is symmetric. Okay, so when j is 0 or 2, that's our total angular momentum. The angular or the spin parts of the wave function are symmetric. But if j equals 1, they're anti-symmetric. And because the total state has to be symmetric, and we know we're in an S state, which means that the space part of the wave function is symmetric, means j is 0 and 2 are allowed, but j equals 1 is forbidden.